Hi, thanks for joining me. Today I'm going to be going over problem 2 from week 1 of the Summer Invariants Puzzle Competition. As always, I'll leave a link in the description below to the Facebook page of the Invariants where you can find more details about the competition. Anyway, this is the problem for today. We have n and k being natural numbers, so strictly positive integers, with n being strictly less than k. And we have these sets a1, a2 all the way up to an. They're non-empty and they're subsets of s, where s is just defined to be the elements 1, 2, 3 and so on all the way up to k. We want to prove that it's possible to colour some of the numbers of S blue or red such that at least one of the elements such that at least one of the elements is coloured, and for all I in 1 through n, the set AI either contains no coloured numbers or it contains both a red and a blue number. So in other words, we have these sets which are subsets of the set S, and what we want to prove is that it's possible to colour some of these numbers such that when we take any of these sets here, either they're all not coloured, or there's at least one blue and at least one red number in that set. Anyway, if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so the key to this solution is the fact that n is strictly less than k, and in fact the statement doesn't hold in general for n being bigger than or equal to k. Anyway, what we want to do is consider our sets a1, a2 and so on, and I'm going to call the generic one just al for now, and then that's all the way up to an. And what we want to do is consider a system of n equations. So for each of these guys here, what we want to do is consider the equation, the sum from I in the set, so I in al of xi equals 0. Now these xi's here are just sort of unknown variables, so you know they'd be like x, y, z, so normally, so we kind of have a system of simultaneous equations in these xi's, so x1, x2 all the way up to xk. So these xi's are from this set here, or sorry, the i's are from this set here, which is just s, and we've got one equation for each of these ai's. So this one, you know, we've got n equations essentially in k variables, and now going back to this thing here, we've got n equations in k variables. Because n is strictly less than k, that means that there is a non-trivial solution to this set of equations here. So n is less than k, we've got n linear equations in k different variables, and because n is less than k, we must have a non-trivial solution. And one way to kind of convince yourself that that's true is because if you kind of if you think of this in a matrix, or think of this in matrix notation, this sort of set of simultaneous equations, you can add on k minus n 0 rows to kind of make it a square matrix, and that square matrix, because it's got 0 rows, will have determinant 0, and hence will have some non-trivial solution. So there exists some x tilde i's, like so, and this is for I in S, such that not all xi's are 0, so not all xi's are 0, but also they satisfy this guy here. Now, what are we going to do? Why does this solve the problem? Well, if we just colour I red, if and only if x tilde I is positive, and do a similar thing, colour I blue, if and only if x tilde I is negative, and then leave it uncoloured if x tilde I is 0, I claim that this satisfies our problem. Why is that the case? Well, firstly, notice that there's at least one coloured element, because there must be at least, because this is a non-trivial solution, there'll be at least one of these x tilde i's being positive or negative, so we have at least one coloured number. But if we go back to this thing here, if we look at any set, say al, so a generic set, because these xi's satisfy this, then that means it satisfies sort of this equation here. So either all the xi's are 0, which corresponds to each element in the set being uncoloured, which is allowed, or this guy is 0 and there are some non-zero elements, so some of these xi's are non-zero, in which case we must have at least one positive and one negative element, which corresponds to having one red, or at least one red and at least one blue. So I hope that all makes sense, but essentially the key to that argument is the fact that n is less than k, so we can find a non-trivial solution and then colour the elements according to that non-trivial solution. So either each set is not coloured at all because of the fact that you'll have one positive and one negative, or at least one positive and at least one negative, therefore you'll have at least one red and at least one blue. I hope that's all made sense. I thank you for watching. Do check out some of my other solution videos as well, and check out some of my other maths content while you're there as well. Anyway, thank you for watching. I'll catch you in the next one. Have a great day.